So let's start by having a look at the key property of a function. What is its domain? So what we're asking is, what is the domain of a power series? Or what does that mean? We have a polynomial, right? So isn't the domain of a polynomial all real numbers? Well, remember, this is not quite a polynomial, right? It's an infinitely long polynomial. So yes, we're going to be able to compute it as long as that series converges. So another way of asking this question is, for what values of x does the series converge? Now, we can see quite easily that a power series always converges if x is equal to c, right? Because if x is equal to c, what does the power series end up being? Well, all the powers of c minus c are just 0. The only one that is going to be left is a 0 if we assume that 0 to the power 0 is equal to 1, which is an assumption that we will be making in the context of power series. Okay. So in that situation, the series is definitely going to converge. Okay. But where else? Are there any other values? How far can we go? Is the domain going to be a simple set, or is it going to be a complicated one? Will we have to look for points in the domain all over the place? Turns out that it's not the case, that the domain of a power series turns out to be a very simple matter. In fact, now let's say that this is the real line. So we know that this is C. If this is C, the center of convergence, then the series definitely converges at C. Okay. So now it turns out that for any power series, there is always a non-negative number r, such that the series is going to converge absolutely if x is between C minus r and C plus r. So we're going to get convergence on an interval, which is not only just an interval from here to there, but it's also an interval centered at C. So as long as we're between C minus r and C plus r, we definitely have convergence, and notice it's absolute convergence. However, if we are outside of that interval, then we're going to have divergence. Does that sound familiar? It should. Anyway, I'm going to give you proof in a minute of this fact, and so you'll see why that is true. But this makes the situation quite easy, because again, what that means is that in order to find out what the domain of a power series is, all we have to do is look for this thing that we're going to call, of course, the interval of convergence. In fact, let me give you a little bit of terminology. This number r is called the radius of convergence, and the interval on which we have this convergence, of course, is called the interval of convergence. By the way, this number r is called the radius of convergence because, again, it's equal distance on both sides from C, but also because when you're going to study functions of several variables, you're going to have something, a result similar to this when it comes to series involving two variables, and those are going to be convergent on a circle, which has a certain radius. Okay. And so that's where the name comes from. Now, this is a pretty strong statement, right? I mean, remember that I'm saying for any power series, it doesn't matter what it is, right? It doesn't matter what the ANs are. Okay, this is always going to be true. It's a very powerful, very general statement. So we better have a look at the proof. So let me show you why that property about the interval of convergence is true. I'm actually going to show you only under one situation, which is pretty much the core of the argument, and then we're going to say something about other situations. So let's say, first of all, let's assume that the limit as n goes to infinity of the absolute values of an plus 1 over an is some number L which is greater than 0. Okay. Now, this may look like a very limiting condition, but in fact is not. What I'm going to show you in terms of the proof is really the proof even in the situation when that does not happen. Again, I'm going to say something about the technicalities involved when this is not true after I'm finished the proof. So let's assume that that is true. Okay. Then what we're going to do is we're going to use the ratio test on the series. Okay? Remember, the ratio test is a test that very simply tells us whether the series is convergent or not. In fact, if we use absolute values, it will tell us if the series is absolutely convergent or not. Okay, so that's what we're going to do. We're going to look at the limit as n goes to infinity of the absolute value of the ratio of the n plus first term, which will be an plus 1 times x minus c to the n plus 1, divided by the nth term, which is an x minus c to the power n. Well, there is the obvious simplification that we can do that of canceling powers of x minus c. That leaves us with this expression. X minus c does not involve n, so it can be taken out of the limit. And now we're left with the limit as n goes to infinity of the absolute value of n plus 1 over n. And we have said that that's going to be some number L. All right. So this is the limit given to us by the ratio test, and the ratio test tells us that if that quantity is less than 1, we have absolute convergence. We have convergence, but since we have done the calculation on the absolute values, we actually have absolute convergence. But what does that mean in terms of x? Well, let's see. If x minus c in absolute value times L is less than 1, that means that x minus c is going to be in between negative 1 over L and 1 over L. If you're not convinced of that, you may want to pause and work out the algebra of this step. But if you believe that this is true, if you simply add the c to all three pieces of this inequality, we end up concluding that x is going to have to be between c minus 1 over L and c plus 1 over L. Remember, L was a positive number, not 0. So if I look at these two quantities, they're also going to be positive numbers, and I'm going to call them R. And here is your radius of convergence. So what have we said here? As long as x is between c minus r and c plus r, then the series is going to be absolutely convergent, as we mentioned. On the other hand, if that limit is actually going to be greater than 1, which means x is going to be outside of that interval, the ratio test also gives us a conclusion, namely that the series is going to be divergent by the divergence test. And that's the proof of the claim.